Welcome to the University of Kentucky's Center for Applied Artificial Intelligence. Visit us online at caai.ai.uky.edu to learn more.
Hi, I'm Emily Collier with the Center for Applied Artificial Intelligence at the University of Kentucky. In our last video, we explored the evolution of AI technologies and the underlying deep learning core that powers modern AI. Now, we're going even deeper into the foundation that fuels everything: data. In this video, you'll learn about why data is the lifeblood of AI, how its quality impacts fairness and reliability, and why diversity in datasets is essential for systems that serve everyone. If intelligence is the goal of AI, then data is its lifeblood. Every prediction, every pattern, every intelligent behavior you see from an AI system, it all starts with data. And it's tempting to think that an algorithm is what makes AI powerful. But the truth is, even the best model can't make sense of bad data. As researchers like to say, garbage in, garbage out. And what this means is that bad input data will not produce an accurate model. And we've seen this play out in the real world. Voice assistants like Alexa or Google Home have been found to be significantly less accurate at understanding people who speak English with non-American accents. Not because the algorithms were fundamentally flawed, but because the data these assistants were trained on consisted predominantly of American English speakers. So the bias wasn't in the code, it was in the data itself. So why does data matter so much? Because AI doesn't invent knowledge. It learns from examples. It learns from the data that we feed it. And this is known as a model's training data. These training sets are the data sets used to teach AI systems how to perform specific tasks, like recognizing objects, interpreting text, or predicting outcomes. If those examples are incomplete, biased, or messy, the AI will reflect that. So let's think about this through 3 stages: how we collect data, how we prepare it, and how we apply it. Imagine teaching a student about the world but only showing them a narrow slice of it. If they only saw one kind of patient from one kind of community or one kind of environment, their understanding would be limited, maybe even harmful, if used as a generalized tool rather than one meant specifically for a narrow specialized purpose. An AI learns the same way. And here's where it gets nuanced. Sometimes you want a highly targeted dataset for a highly specialized model. A model trained exclusively on chest x-rays from smokers over 60 would be excellent for lung cancer screening in that specific population. But if that same model were applied to pediatric care, it could be dangerously inaccurate. So the key question during data collection is, who will this AI serve? If it's meant to serve everyone, your training data needs to reflect that diversity. If it's designed for a specific use case, your data should match that target, and you need to be explicit about those limitations. This also raises an important consideration: the relationship between data quality and data quantity. It's tempting to think that more data is always better, but that's not necessarily true. A smaller, carefully curated dataset can accurately outperform a massive but noisy one. Quality matters just as much and sometimes more than quantity. Most AI systems today use a method called supervised learning, where the model is trained on examples that show the correct answer. In other words, the data is accurately labeled. But there are other types of learning too, like unsupervised learning, which finds patterns without labeled data, and reinforcement learning, where models learn by trial and error through feedback. The type of learning that you use shapes what kind of data you need. Supervised learning demands correct labels for every example. Unsupervised learning might use clustering techniques to group similar data points together without predefined categories. And this is useful when you're exploring patterns you don't yet understand. And each approach has different data requirements and different vulnerabilities to data quality issues. Once you've collected your data, it needs to be prepared before the model can learn from it. Data cleaning means making sure that the information we feed into an AI is consistent, accurate, and usable. That might mean removing duplicates, correcting errors, or standardizing formats so that the model isn't misled or confused. But data cleaning goes deeper than that. Sometimes you're dealing with class imbalance, when one category vastly outnumbers others in your dataset. So, for example, if you're training a model to detect a rare disease, you might have 99 normal cases for every one disease case. Without correction, the model might simply learn to predict normal every time and achieve a 99% accuracy, while completely failing at its actual purpose. You also have to handle missing data carefully. Do you exclude incomplete records? Estimate missing values? Consider generating synthetic data. Each choice has trade-offs that affect what your model can learn. Labeling means giving meaning to data, like identifying which image contains tumors, which clinical notes describe specific symptoms. Without clear and accurate labels, supervised learning models can't connect the inputs and the outcomes. And then there's bias. Bias isn't always intentional, but it's almost always present. Bias can enter your data in multiple ways. Historical bias occurs when your training data reflects past decisions that themselves contain discrimination. Think of a healthcare algorithm trained on historical spending data. Because patients from underserved populations historically had less access to care and spent less, they were incorrectly flagged as lower risk, which led to these patients receiving less support despite having equal or greater health needs. Measurement bias happens when the data collection process is itself skewed, like a smartphone health app that only collects data from people who own newer smartphones, systematically missing populations without access to this latest technology. If an AI model is trained only on data from one demographic group, it may perform poorly on others. Sometimes, highly targeted models are trained for specific populations, and that can improve accuracy tremendously in those specific contexts. But if those models are applied more broadly, they might not generalize well. If an AI learns from language that often reflects social stereotypes, it may repeat them, even if no one explicitly programs it to. That's why diversity in data, across populations, geographies, and perspectives, is essential for fairness and reliability in generalized systems. In healthcare, this can mean the difference between an algorithm that supports equitable care and one that unintentionally widens disparities. And real-world examples show this clearly. AI systems that read X-rays perform best when trained on data from multiple hospitals, with patients of different ages, races, and backgrounds. Speech recognition improves when trained on diverse accents and dialects. Even environmental models get more accurate when they integrate local data, not just global averages. So imagine comparing two cities with the same name, like Lexington, Kentucky and Lexington, Virginia. Training models on data from each one individually can help tailor more accurate solutions for their specific needs. But here's a critical technical point. When your training data is too narrow, you risk overfitting. This is where the model essentially memorizes the training examples rather than learning general patterns. It performs beautifully on data similar to what it's seen before, but it fails when confronted with anything significantly different. On the flip side, if your data is too sparse or inconsistent, you get underfitting. This is where the model never learns meaningful patterns at all. This is why the match between your data and the intended application matters so much. The best model is one that learns the right level of generalization for its intended purpose. Every example reinforces the same truth. Data is key. So we've seen that data is not just the raw materials of AI, it's the foundation that shapes everything it can learn. The quality, completeness, and diversity of training determines whether an AI system is fair and reliable. So the next time you hear about an impressive new AI model, remember it's not just the algorithm that matters. It's how it was trained and the data it was trained on. In our next video, we'll explore where that data, the AI systems that depend on it, actually live. From local devices to the cloud, and from self-service tools to shared national resources, we'll look at the infrastructure that powers AI research and the resources available to assist those pursuing it. Thank you.